So, next is your second example, example 2, right, this one. So, I hope previous one you might have understood, right, and it's very simple thing, all these things are, right. So, a generating station has a maximum demand of 80 megawatt and a connected load of 150 megawatt, right. If megawatt hour, that is energy generated in a year, is that is annual energy generation, year is 400 into 10 to the power 3 megawatt hour. You have to compute load factor and demand factor, right. So, maximum demand is given 80 megawatt, right. Connected load also given 150 megawatt. Units generated in 1 year is given 400 into 10 to the power 3 megawatt hour. It is given in megawatt hour generated in a year is 400 into 10 to the power 3, right. And total number of hours in a year is equal to T is equal to 8760, right. So, all data are known, right. Therefore, average load you can find that it is annual energy generated divided by the total number of hours. So, it is 400 into 10 to the power 3 divided by T is equal to 8760 is equal to 45.662 megawatt, right. And load factor LF is equal to average load by maximum load. So, average load is 45.662 megawatt and maximum is 80. So, load factor is 0.57, right. And demand factor DF is equal to maximum demand by connected load. Maximum demand was 80 megawatt and connected load 150 megawatt. Therefore, demand factor is equal to 0.533, right. So, this is a simple example, but all this terminology whatever you have used. So, we will take one after another few example such that it will be understandable to you. Next is example 3, right. So, a sample distribution system is shown in figure 5. Figure 5 I will show you later. One of the feeders supplies an industrial load with a peak of 2 megawatt and the other supplies residential loads with a peak of 2 megawatt. Combined peak demand is 3 megawatt. Determine A, the diversity factor of the load connected to transformer, B, the load diversity of the load connected to transformer, and C, the coincidence factor of the load connected to transformer. So, these three things you have to obtain. Now, figure 5 for this example, right. So, it is given this sub transmission system, a transformer is there, this is distribution substation, and this is industrial load, residential load and reserve for future load. This is a diagram, sample distribution system of example 3, right. Now, from equation 7 diversity factor is that, from equation 7 that diversity factor formula is FD is equal to sigma I is equal to 1 to n Pi upon Pc, but here you have two consumers, right. Here it is given, one for industrial, another for your residential, right, industrial and residential. So, n is equal to 2. So, I is equal to 1 to 2 Pi, that is by Pc, that is P1 plus P2 upon Pc, right. So, it is given for both the cases, industrial with industrial load with a peak of 2 megawatt and other supply residential load with a peak of 2 megawatt. That means, P1 is equal to 2, P2 is equal to 2, that is 2 plus 2 and total and combined peak demand is 3 megawatt. So, Pc is equal to 3 megawatt, right. So, 2 plus 2 by 3, so it is 1.333, right. So, this is your diversity factor. Now, from equation 14, that load diversity LD is equal to sigma I is equal to 1 to n Pi minus Pc, n is equal to 2, P1 is equal to P2 is equal to 2 megawatt and Pc is equal to 3 megawatt, right. Therefore, load diversity is equal to P1 plus P2 minus Pc, that is 2 plus 2 minus 3 megawatt, the load diversity is 1 megawatt. And from equation 13, coincidence factor is Cf is equal to 1 upon diversity factor, right, is equal to 1 upon 1.333 is equal to 0.75, right. So, this numerical, these problems are very, very simple, right. Next is we will try to establish a relationship between load factor and the loss factor, although direct is not possible, but we will try to establish some relationship. So, relationship between load factor and loss factor, right. First, before coming to this, in general, loss factor cannot be determined from the load factor, right. So, generally it is directly, it is not possible. However, the limiting values of the relationship can be established, right. So, this is figure 6, it shows an arbitrary and idealized load curve and it does not represent a daily load curve. This is just to establish a relationship, something has been drawn. So, if you take this y axis, first take the load, say this is peak load, for this thing is P2 and off peak load is P1 and its average is, this dashed line is the average load, right, something we have drawn. So, this peak load, that your the duration is from 0 to small t timing, right, and off peak load from your t to t, the duration will be capital T minus small t, right. So, this is peak load P2 and off peak load is P1, average is P average, this is the load curve. This is something had been drawn, it is ideal load curve, right, something has been taken. Corresponding this to that peak load for the system, suppose loss is, peak loss is L2, corresponding this peak load, the loss is your peak loss. This loss also, peak loss also will exist from 0 to t only, because peak load is 0 to t, right. And then your off peak due to for off peak load P1, the loss is L1, right. This is that off peak load L1, right. And then this duration is from small t to capital T, that means t minus t, right. And this is also an average, and this dashed line, blue dashed line is the average loss. So, this kind of a, just to establish, we will try to establish a relationship between that your load factor LF and the loss factor LLF, right. But this is nothing, it is not a reality, but for the sake of for the sake of establishing a relationship, we have made it like this, right. If we do so, then assume that the peak load P2, so I told you peak load is P2, this P2, and corresponding loss is, peak loss is L2, I told you, and at off peak load P1, loss is L1, off peak load is P1 and corresponding loss is L1, right. And the load factor is LF is equal to P average upon P max. Here we have taken that this is some average load line. So, this is my P average divided by P max, P max is nothing but the P2, right. So, this is equation 23. Now, from figure 6, I mean this figure, from this figure, if you see like this, from figure 6, if you see that your P average is equal to P2, its duration is T. So, P2 into T, small t plus that duration of P1 is, this is now low load level P1, duration is capital T minus small t. So, plus P1 into capital T minus small t divided by total duration 0 to t, that is your divided by t, right. So, that is your P average. Therefore, from equation 23 and 24 we obtain that is your load factor is equal to this P average, you substitute here, right. If you substitute here, then load factor is equal to P2 into T plus P1 into capital T minus small t divided by P2 into capital T, right. I hope this part is understandable to all of you, right. Next, that means this load factor LF is equal to, I am rewriting once again, P2 plus P1 into T minus capital T divided by P2 into T. That means this one, it can be written as P2 into T divided by P2 into capital T plus P1 into T minus T divided by P2 into T. This way you can write. Therefore, LF is equal to P2, P2 will be cancelled. So, T by T plus it will be P1 upon P2 into T minus T by T, right. That means this LF. So, here we are writing this LF is equal to, therefore, whatever I wrote, that T by small t by capital T plus P1 upon P2 into T minus T upon T. This is equation 25, right. Similarly, the loss factor is double LFF, right. LLF is equal to L average upon L max, right. So, from this figure, it is your this line is L average upon L2, right. L2 is the peak loss. That means during peak load, this is the peak loss L2, right. So, that means L max is equal to L2. This is equation 26. L max is equal to maximum power loss is equal to L2 and L average is equal to average power loss. From figure 6, similarly, we will obtain same thing, that peak loss is existing from 0 to T. So, L2 into T plus your L1 is that your off peak loss. So, it is L1 into T minus T divided by the your T, right. So, that is your L average, total duration is T. So, that is your equation 27. Similarly, this loss also you can write. So, this L average you substitute here, you substitute this L average expression in 26, here you substitute. If you substitute here, then you will see, that is why I am writing from equations 26 and 27, we get LLF is equal to L2 into T plus L1 into T minus T divided by L2 into, same as before. So, this is 28, right. Now, where small t is the peak load duration and capital T minus small t is equal to off peak load duration. Now, the copper losses are the function of associated load. We know that your power loss is in general I square R loss, right, and I means the current, and hence the current is depend on the load only, right, are the function of the associated loads. Therefore, the loss at off peak and peak load can be expressed as, at off peak hours loss is L1 is equal to some constant into P1 square, because because loss actually is proportional to the square of the load, I mean approximately proportional to the square of the load. Of course, load have different characteristic, but for the establishing this relationship, the loss is, so off peak hours load is P1 and loss is L1. This K is the constant of proportionality, it will remain same for both, right. So, L1 is equal to K into P1 square. Similarly, at peak hours loss L2 is equal to K into P2 square, right. This is quite valid, this is quite true, because loss is proportional to I square and I depends, the current depends on the load, hence the loss also to some extent related to the square of the load, right. Therefore, this L1 is equal to K into P1 square, right, and L2 is equal to K into P2 square. You substitute in equation 28 this L1 and L2 expression, you substitute here in equation 28. If you do so, therefore, we are writing from equation 28, 29 and 30. Therefore, from equation 28, 29 and 30, we get LLF after simplification, LLF is equal to small t by capital T plus P1 upon P2 whole square into T minus capital T minus small t divided by capital T. This is equation 31. You substitute and just simplify, same as before, right. Therefore, loss factor is expression is this one, right. Now, by using equation 25 and 31, that means this equation, that means using this equation, and this is the load factor your equation, and this is the loss factors equation. Using these two equations, we will try to establish a relationship between load factor and your loss factor, right. So, how to make it? So for 3 different cases we will consider. From that we will try to establish some relationship. Case 1, off-peak load is 0. That means there is no off-peak load. That means if no off-peak load, then P1 is 0. That means your L1 is also 0. Loss off-peak load P1 0 means that off-peak load 0 means off-peak loss is also 0. Therefore, from equation 25 and 31. So equation 25 is this one. So here you put P1 is equal to 0 and your what you call L1, your if you put P1 is equal to 0 in this expression, then what will happen that your LF will become, if you put here, just let me write down. If it is take this equation 25, for the case 1 is off-peak load is 0. That means this case 1 off-peak load is 0. That means if P1 is equal to 0 and then L1 is also 0. Therefore, your equation your 25, equation 25 here it is LF is equal to T by T plus P1 by P2 into T minus T by capital T. But here P1 is 0, that means LF is equal to small t by capital T, right. Similarly, in equation 31 is this one, this is for LLF. Equation 31, this expression is there, loss factor is equal to small t by capital T plus P1 by P2 whole square into T minus T by capital T. But P1 is 0, if you put P1 0, this term will not be there. Therefore, loss factor also is equal to T by T, right. This one, here also this one. That means for the case of where off-peak load is 0, that means load factor is equal to loss factor. That is why here we are writing that if off-peak load is 0, then therefore equation from equation 25 we will get that LF is equal to, this is from equation 25, LF is equal to small t by capital T, and from 31 also we get this LLF is equal to T by T. Therefore, this thing and this thing they are same, LF is equal to LLF. Therefore, this we have LF is equal to LLF is equal to it is your T by T, small t by capital T, right. Therefore, it is your equation 32, that is load factor is equal to the loss factor and they are equal to small t by capital T is equal to constant, right. This is for the case 1. This case 1 we have assumed, right, because we have to establish some relationship, that is why we have assumed, right. Similarly, now case 2, very short lasting peak, right. In this case the time t tends to 0. Therefore, equation, if you look at equation 25, just hold on, equation 25, when t minus your t very short lasting peak, that means here t tends to 0. Hence, in equation 25 that t minus t divided by t tends to 1. Therefore, we can make it loss factor is equal to this thing from equation 25 and 31. Come to this 31. Where is equation 31? This one, right. When t tends to 0, right. Where it has gone? Yes. When t minus t upon t your this tends to 1, right, and LLF is equal to your here t tends to 0. So, from these two condition you will get that loss factor is equal to load factor square. You take t tends to 0 and equation 25 and 31, if t tends to 0 means t minus t upon t tends to your what you call your 1, right, and in that 20 and in that equation your load factor equation when, just hold on, I will make it here such that things will be easier for you, right. First you consider 25, right, and the condition is that your case 2, that very short lasting peak, that means t tends to, first you come t tends to 0, right, that means t minus t by capital T, it tends to 1.0, because t tends to 0, that this term is tends to 1. Therefore, equation 25, you take equation 25, it is load factor is equal to T by T plus P1 by P2 into T minus T by T. As t tends to 0, this terminology tends to 1 and this is 0, that means LF equal to P1 by P2. This is your load factor for this condition. Similarly, if you look at equation 25, right, not 25, 31, that loss factor expression. That loss factor expression is, I am writing here, LLF, this is equation 31, it is T by T plus P1 by P2, right, whole square, then T minus T by capital T. As t tends to 0 and this t minus small t upon capital T tends to 1, that means LLF is equal to your P1 by P2 square. This term will vanish and this tends to 1, it will P1 P2 whole square, right, and your LF is equal to P1 upon P2, that means this one is equal to load factor square. That means loss factor for this condition is equal to square of the load factor. Therefore, we are writing this one, that here t tends to 0, therefore, from equation 25 and 31, loss factor is equal to load factor square. This is equation 33. Now, another condition is when load is steady, that is here t tends to t, constant, load is steady, t tends to t, that is the difference between peak and off peak load is negligible, almost constant. In that case, you will get same thing from equation 25, you will get loss factor is equal to load factor, right. So, that means your small t is tends to your capital T, right. Therefore, load is steady, in that case you will get it that loss factor is equal to load factor. That means one condition we got 3 different conditions, but therefore, in general that is coming like this. First condition whatever we saw, that loss factor is equal to load factor, then another condition we took, it is your equal to LF square. So, generally load factor is less than 1. So, and therefore, loss factor will be greater than LF square, square of the load factor, but less than your load factor. So, greater than square of the your LF square and less than LF. So, this is the this is that your what you call the condition for the loss factor, something can be established, but in general it has been observed that the loss factor cannot be determined directly from the load factor, it is not possible, right. However, an approximate formula to relate the loss factor to the load factor as that loss factor is equal to 0.3 into load factor plus 0.7 into your load factor square. This equation or this terminology is used by many, particularly for the for the city areas or this thing. This formula is quite valid, but if it is a rural areas, right, rural feeder or this thing, in that case instead of 0.3 it comes 0.2 into LF plus 0.8 LF square, right. So, and approximately it has been found that these equations work relates well between loss factor and the load factor, right. So, this is the relationship between loss factor and the load factor. These are all these general thing I am telling in at the beginning, right. After that we will see something different, but one should be familiar with all sort of terminology, loss factor, load factor, everything. But for rural feeder or rural load, this instead of 0.3 it is 0.2 they take, and it is 0.8. Some other relationship also comes, because loss factor or load factor depends on the load growth also, which I will not tell anything here, but it depends on the load growth also, right. Next is your load growth. Actually, whenever you see any sort of thing, load is increasing, right, continuously, right. So some cases, some places maybe it is at a rate of 3%, 4%, 5% annually, or even more. So load growth is always there. So if load increases, so generally your load increases means demand is increasing, right. And demand increases means, suppose in a particular network load demand is increasing means that you need to supply that load. So in that case, if load increases, you have to think many things, because power loss will increase, then every year load is increasing, that means voltage will also at different point will go down, right. All these things you need to maintain at an appropriate level. So load growth is the most important factor. It is inevitable that load will increase, right. Influencing the expansion of distribution system, forecasting of load increases is essential to the planning period. So one has to forecast the load, that how things will happen. What I am telling you here just the preliminary thing or basic thing, right. But load growth is the important part of our power system, right. So if the load growth rate is known, right, then load at the end of the mth year is given by, so suppose Pm is equal to P0 1 plus G to the power m. This is equation 37, where Pm is the load at the end of mth year. Suppose today at this point it is the base year, that is initial load, right. So suppose this 2017, at this point load is P0, next year at this time it will be suppose it is increasing at a rate of say 5%. So G is the annual load growth rate, say G is the 5%, and it is number of years. That means Pm is the load at the end of the mth year, P0 initial load at the base year, G is the annual load growth rate, and m is the number of years. For example, suppose your Pm we are writing that P0 1 plus G to the power m, right. P0 is the load at the this thing base year, that means at this, suppose this year, right, and G is the annual your load growth rate. So suppose G is equal to 5%, that is 0.05, right. Therefore your Pm is equal to, it can be written as P0 1 plus 0.05 to the power n, that means Pm is equal to P0 1.05 to the power m, right. When base year, when m is equal to 0, Pm is equal to P0, it is automatic. Now when m is equal to 1, Pm is equal to P0 into 1.05. When m is equal to 2, Pm is equal to P0 into 1.05 square, and so on. Similarly, for m is equal to 3, Pm is equal to I can put when m is equal to 1, P1 when after first year, when m is equal to 2, after that P2 is equal to this one. Similarly, when m is equal to 3, P3 is equal to your P0 1.05 cube, right. Then suppose P0 if you take say 100 kilowatt for example, right. So first year load will be 100 kilowatt, next year it will be 100 into 1.05, right, 105. Now second year it will be 100 into 1.05 square, third year it will be 100 into 1.05 cube, and so on. This is that load growth rate formula, right, that Pm is equal to P0 1 plus G to the power m, right. Next, actually take another example. A substation, it supplies power to 4 feeders, right. Feeder A has 6 consumers whose individual daily maximum demands are 70 kilowatt, 90 kilowatt, 20 kilowatt, 50 kilowatt, 10 kilowatt and 20 kilowatt, right. while maximum demand on the feeder is 200 kilowatt. Similarly, for feeder B, it supplies 4 consumers whose daily maximum demand are 60 kilowatt, 40 kilowatt, 70 kilowatt and 30 kilowatt, right, while maximum demand on feeder B is 160 kilowatt, right. Feeder C and D have a daily maximum demand of 150 kilowatt and 200 kilowatt respectively, while the maximum demand on the station is 600 kilowatt, right. So, in this case you have to find out, right, diversity factor. I didn't write here that what you have to obtain. You have to find out diversity factor for feeder A and feeder B. So, from equation 6, diversity factor is FD is equal to sum of individual maximum demands divided by coincident maximum demand. For feeder A, coincident maximum demands given 200 kilowatt it is given, right, and therefore, you sum up individual maximum demand. So, 6 are there, 70, 90, 20, 50, 10 and 20, you add, they are all kilowatts, divided by coincident maximum demand 200 kilowatt. So, for feeder A, diversity factor is 1.3. Similarly, for feeder B, 4 consumers are there, 60 plus 40 plus 70 plus 30, all are in kilowatt, and their peak is 160. Therefore, diversity factor for this one is 1.25, right. So, next one is for feeder B, then diversity factor of the 4 feeders FD is equal to, then add 200 plus 160 plus 150 plus 200 divided by 60, it comes about 1.183, the diversity factor of the 4 feeders, right, feeder A, feeder B, and for the 4 feeders. So, for feeder B 1.25, and for the 4 feeders, other 2 feeders data are given. Feeder C and D have a daily maximum 150 and 200, here we have made, other 2 are 200 and 160, and maximum demand of the station is 600 kilowatt. So, diversity factor of the all 4 feeders will be 200 plus 160 plus 150 plus 26, this is 1.183.